Esse aqui para passar, né?
E isso do meio.
E a bateria tá...
Tenta. Ver se funciona esse laser. Não funciona.
Tá. A bateria tá piscando. Não tem problema.
Acho que não.
Eu sou o último.
Okay. Let me present our last speaker for today. Professor Panters Rodríguez Bermúdez from Federal University of Fluminense in Volta Redonda. He will speak about vertical two-phase flow under the action of DIRAC-DELTA source in a porous medium.
Thank you very much. First, I would like to thank the organizers of the conference by the invitation. It's always very nice to come back here and see a lot of friends. I will talk about vertical two-phase flow under the action of a Dirac-Delta source in a porous medium. This is a collaboration with Diego Monteiro, my ex-student from the post-graduation program in computational modeling that we have there at UFI in Volta Redonda, and also with the Professor Victor Manuel Martins de Matos from Universidade do Porto, Portugal. We study a vertical two-phase flow under the action of a point injection at z equal to 0. We assume that there is only one spatial dimension, and others physical hypotheses, for example, the porosity and the permeability of the rock are constants, the fluids are immiscible, there is no mass interchange between the phases. We also assume that the fluids are incompressible and have distinct densities, and we neglect capillarity pressures effects. After considering the mass balance law for each phase and taking into account the Darcy law for vertical flow for seepage velocity, we also consider quadratic permeabilities for both of the phases. It is possible to show that for this problem, the total Darcy velocity V is not constant. Indeed, V has a spatial discontinuity at z equal to 0, represented here by this Heaviside function. And the parameter Q is the sum of the Qi, where Qi represents the injection rate of each phase I. After perform a non-dimensional analysis, we obtain two balance laws for the phases. The source terms appears here are proportional to the delta function. The flux function have a discontinuity at z equal to 0, affecting the convective part of the flow, but not the gravitational part of the flow. We also notice this parameter Q appear here, multiplying the Heaviside function. Of course, we can neglect any one of the equation in 3 because they are redundant, but the equation to be neglected will be chosen depending on the situation that we have of injection. For example, for a point injection of pure water, we will have QO equal to 0 and QW equal to the total Q. So in this case, it seems natural to neglect the equations of the phase water instead of neglecting the equation of the phase oil. Taking into account the discontinuity of the flux function at z equal to 0, we split our analysis in two regions. For z negative, we will have a conservation law here with a left flux function denoted by FR. And for positive z, we will have another conservation law here, now with flux function denoted by FR. Of course, the action of the source term, which is all concentrated at z equal to 0, will appear in this jump condition, where capital SL and capital SR denotes the left and right states of any discontinuity which is stationary at z equal to 0. In general, these states are distinct, and they are very important in the construction of these Riemann solutions, as we can see in the next slides. We also remark here that we use the notation of superscript 0 for initial Riemann data. The general structure of the Riemann solutions consists of two groups of waves. Elementary group of waves are composed by rarefaction, non-static shocks, and eventually left or right characteristic shocks. We also use this notation STS for static shocks. The first group of waves travel with negative speeds, so they travel upward in the reservoir, and is obtained through the classical Olenek construction for the flux FL, while the second group travel with positive speeds, and it can be obtained through the classical Olenek construction for the right flux function FR. The key point here is to find these states, the left and right states of the static shock, in order to obtain a sequence of waves that enter this sequence would satisfy in some way an entropy condition. So we will establish the connection between the left flux function and the right flux function using these states here. So we will focus our analysis in how to obtain these states of the static shock. They must satisfy not only the jump condition, but also an entropy inequality here, where we are using this notation operator succeed when the derivative of the left flux is positive, or in the case to be equal to 0, but one of the limits here have positive signs. In another way, we use this notation with operator precede if the derivative is negative, but in the case in the case that it is equal to 0, but one of the limits here has a negative sign. These entropy conditions are the same that the ones founded by Kasketer in his paper. In the works of Kasketer, he deals with discontinuity also in the flux function, but is a other kind of discontinuity. A discontinuity this discontinuity of Kasketer appear as a consequence of heterogeneity in the medium instead of a consequence of injection, like in our case. We will show the procedure to construct the solutions for in a special case that is very important in applications. For example, when we have a pure water injection, we will show only the solutions for the case oil heavier than water. The second case, the other case, can be the solutions of the other case can be obtained in another way. Here, as we have QO equal to 0, the jump condition reduced to this form here. So we can see that this means that the states SL and SR will be geometrically connected by an horizontal line joining the left flux function and the right flux function. Typically, we have a flux function as in the picture here. Blue, the one in blue is the left flux function. The one in color red is the right flux function. there are some states that are important in the construction. For example, the maximum point ML and MR of the flux functions, and other states which can be connected to these ones and with the initial data by straight lines, horizontal straight lines. It's important to notice that in the general injection case, the connecting lines between the flux functions in general will have non-zero slope. So this is a particularity of this injection case here. We prove this theorem to obtain the entropy solutions. There exist 4 cases of Riemann solutions depending on the localization of the initial data SL0 and SR0, and there exist 4 regions for this initial data. In each one of these regions, the solution will be the same structure. The region 1 and region 2, here in the picture, they depend only on the parameters of the flux function, but the region 3 and region 4 they can change with the left Riemann data here. For example, for a Riemann data lying in the region 1, we prove that the only entropic wave to connect by an horizontal line the both flux functions will be with left state here at the maximal point in the left flux function. So SR will be this MR, is the only entropic possibility to connect these flux functions here. So in this case, for example, if we have left Riemann data equal to 1, right Riemann data equal to 0.1, we will have the following sequence of waves: a shock traveling with negative speeds, followed by a rarefaction up to the state MR of maximum, followed by the static shock joining MR with SR minus here, and then we followed by a shock with positive speeds. So in this case, we have the 2 groups, the first one with negative speeds and the second one with positive speeds. Here to the right side, we show a qualitative profile of the solution. It's not the exact solution, since we are approximating the rarefactions by straight lines here. For a second case, Riemann data in the region 2, it is possible to prove that the right states of the static shock will be exactly the right Riemann data. The only way to connect these flux functions for this region will be finishing the sequence of waves by the static shock. So in this case, there are no waves traveling with speeds with positive speeds, only wave traveling with negative speeds. In this example, in which we have the left Riemann data equal to 0.5, the right Riemann data equal to 0.9, we will have only a shock traveling upwards in the reservoir with negative speeds, and the static shock here joining the states S double star with the right Riemann data. In another way, for Riemann data in the region 3, it is possible to show that the first wave of the sequence will be the static shock, because we prove that the left state of the static shock will be exactly the left Riemann data. So in this case, on the contrary of the previous case, we only have waves traveling with positive speeds after the discontinuity at z equal to 0. For the fourth case, the structure is similar to the second one, so I will skip the explanation. And now we also are interested to solve numerically this problem, because we keep in mind the initial goal for us is to apply, to solve the analogous problem for three phases, for three-phase flow, vertical three-phase flow. So it is very interesting for us to have a finite difference method which works well for this kind of problem, having having this continuous flux function and a stiff source term. Talking about this with the professor Eduardo Abreu from Unicamp, he told me about the works from his student, doctoral student John Sepulveda. They constructed a family of waves by the formulation of Lagrangian-Eulerian formulation, and these kinds of methods have the properties of being locally conservative and deal properly with the complex question of the nonlinear balance between the numerical approximation of the hyperbolic flux and the source term of the balance law. We used the method that they call Lebesgue 2. This method has this scheme of finite difference, where F denotes the numerical flux function and Q are the source terms. And they also prove a CFL condition for the stability of this method, and provide a way to implement this method for this continuous flux function. In this case, F will be the left flux function and H will be the right flux function. We also must to deal with the regularization of the source term, because they are these terms is very stiff, and typical regularizations commonly used in the practice does not work properly. So the same Eduardo told me also about this work about from Enquist and collaborators. In this paper, there appear some ways of regularize the delta function. All of them satisfying certain momentous condition for of certain orders. We take this approximation, this linear approximation for the function phi here. This approximation will satisfy a second order moment condition, and we can see that putting together the Lagrangian-Eulerian method from Sepulveda and Abreu, together with the regularization and Enquist, we obtain good results. Here we have the numerical solutions to the left, and to the right we show the entropic profiles, approximated qualitative entropy profiles obtained by the analytical method. So we, for several Riemann data in each of the regions, we have the numerical method matching with the analytical solutions. And this case is for oil, for water heavier than oil. So in this case, we also show the solutions. And we can conclude that as follows. First, we extend the Euler's construction method to obtain analytic entropic solution for our problem. Second, second point is that the Lab-2 method performed well, capturing the stationary waves, shock waves, and rarefaction waves in the solutions. The numerical regularization for the DIRAC-DELTA, it was crucial for good results. And the matching between the entropic analytical solutions and numerical results can be viewed as a numerical evidence for the convergence of the Lab-2 method to entropy solutions. There are no theoretical results about convergence of this method in the case of discontinuous flux and singular source term. As future works, we have in short term, we want to study the vertical three-phase flow on the direction of a Dirac-Delta source. We thanks to Professor Eduardo Abreu and John Alexander Sepulveda by their important contribution to this work. We thank also COPPE and UFI for the support. Here, some of the reference that were important in our work. Thank you very much.
Thank you very much.